So the title of our talk is Deep Spatial Context, and I will focus on digital pathology, even though the method that I'm going to introduce to you is general. And the work is done together with Elżbieta Sienkiewicz and Przemysław Biecek from Warsaw University of Technology and Mei Hong from Harvard University of Medicine. Okay, shortly about me. So I'm a PhD student at Warsaw University of Technology. And my focus is mostly on deep learning in medicine, recently histopathology. And I really like to investigate the importance of contextual information. And actually, this is something that I'm going to cover today. And I am working at MI2 Data Lab at my university. And I gain experience in AI at various universities. Okay. So now moving to the main part of the presentation, which is Deep Spatial Context, in short, DSCon. So there are three main components of this. The first one is histopathology. Then it's deep learning, and lastly, spatial regression. And this is the order of the topics I'm going to cover in the talk. Okay, let me start with histopathology. I guess maybe it's not that obvious for you. What does it mean actually to tackle with such data? So what problems do we have once we use whole slide images, and how we actually can get such data? So in general, physician cuts out parts of our tissue, let's say, and then histopathologists, they observe the tissue under big resolution within the microscope. So we have several problems with this kind of data. First of all, data is huge. It's like tens of thousands of pixels over tens of thousands of pixels. And also, often we have only one global label per this whole slide image. So you may expect that it comes with some challenges. First of all, the technical ones. So that we have huge images, and also they don't have standardized size. So once we want to load these images to memory, it's not feasible most of the time, and also it's not feasible to process them at one go, but we have only one label. So we have to find the solution, and I'll go into that in a moment. And apart from the technical problems, we also have another problem that also makes just the task difficult, is that we have to inspect our tissue, or the tissue taken by a physician, very carefully, because we can see like individual cells. So we have to analyze it carefully, and this is why the work of histopathologists is difficult, and this is also why training an appropriate neural network system is difficult. Okay, but actually, what is actually important for the talk is that there are some solutions already to this problem, and one of the most common approaches is called CLAM. It was introduced in 2021. And how it works. So we have our big image, and first what we do, we cut it into patches. And then each patch is an input to the feature extractor. And as a consequence, we get a set of feature vectors. And later on, we have to remember that we have just one global label. So we cannot do classification per each patch. So what we do, we try to aggregate the information from each patch so that we can later on perform just classification. So we apply attention module where we do a weighted sum over all feature vectors. And we weight these feature vectors by the attention scores that are trainable. And so we get a representation of the whole big image, and we later on apply multi-layer perceptrons to perform the classification. And our goal in this task is just to decide whether there's a tumor tissue within the big image or the whole tissue is normal. Okay, so as you may think, just because we have attention scores per each patch, so how important it is once doing the classification, the CLAM method itself is already explainable by design. So here you can see some heat maps, and these are not achieved using heat map-based XAI methods like LIMES or so on. And this is just the visualization of the attention scores per each patch. So some of you may think, Okay, so it means that we can understand the method, the system itself, so maybe there's nothing to do more. But actually, it's not the thing. And our idea, after some discussions with histopathologists, is that maybe we should analyze the model even further from a little bit different aspect. So what we have learned from the experts is that they analyze lesions in both global and local aspects. It means that they pay attention for the whole structure of the tissue, so this is the global one, and also to the individual cells. And our question was, do neural networks take into account the spatial context? And maybe now you already see the connection between the title of the talk and what I'm going to cover in the next minutes. Okay, so the idea is that we're going to investigate the CLAM model through the lens of spatial regression. But before I move into it, let me give some preliminaries. Okay, so let's start with something basic, which is linear regression. I guess most of you know what does it mean and why we use it, but maybe you don't remember exactly what assumptions are behind. So one of the assumptions is that observation and residuals should be independent of each other. So now let's focus when actually it can be violated. It may happen that we have spatial data and there are some spatial correlations between different samples. And here we have an example on this graphic. Here we can see the crime rate in New York City, in different regions of New York City actually. And what we can see is that there are some clusters. So there are some regions, like the neighbors, where this ratio is similar, the high one, let's say, and there are some other regions where this ratio is small. So here we can observe spatial correlation. And we want to see whether within our patches of the histopathological image, there are also some kind of clusters, and whether the neural network can actually see it. Okay, so we know that sometimes we cannot use linear regression. So what we can do, we can use spatial regression. And in this talk, I'm going to focus on 3 variants of it. And I will not dig into the details of these methods, but what's important is that, first of all, it looks kind of a normal regression, linear regression, but there are some additional terms. In the first equation, we can see that we have the W matrix. And this metric is called spatial weight matrix. And what is important that this matrix is visible within different parts of the equation in each of the 3 methods. So in the first method, we apply this matrix to features. In the second, to labels, and lastly, to residuals. And this is important, and I'm going to go back to the topic in a moment. But first, let's focus on what this matrix is actually. So we can think of it as a sparse matrix, so it's full of zeros, and there are some ones. And where we put these ones is that we actually analyze where are the neighboring patches. In the most trivial scenario, we take into account only the adjacent patches, some regions. So if the 2 patches are close to each other, we put 1, otherwise it's 0. But in this trivial example, we can analyze only at most 8 neighboring patches. But we can do it also differently, so we can make it more general and think of it as searching k nearest neighbors. And if particular patches are within this group, then we put 1. So this is kind of the matrix that we're going to use to specify that some patches are close to each other. Okay, so we already know at least a bit what spatial regression is, but now why we actually care and why we are going to use it. So the idea is that we want to check whether spatial relationships are maintained within the deep learning model. And we're going to evaluate it using spatial regression. To make it even more clear, here is a, let's say, graphical abstract. So what we can see is the already trained CLAM model. So nothing changed. We trained the model, we have it, and now we want to verify how does it work and whether it takes into account the spatial context. So what we do, we extract from the already trained model Okay. From the already trained model, we want to extract the features and also the assigned attention scores. And this is the input to the regression models. And we apply it, actually two kinds of spatial models. So we have this spatial regression, and we have the normal linear regression. And we are going to get some performance metrics later on, and we want to compare it. So whether there's any boost when we apply spatial regression over linear regression. Because if there is a positive boost, it means that the spatial regression is important, so that the spatial context actually matters. And this is the idea. And this difference between the two performance metrics is actually something that we call measure of spatial context. And we have three different types because of three different spatial regression models that we use. Okay, so now let me move more to some details. So that was already the idea behind, and now let's see what we can get by the use of the method. Okay, so in order to use a deep spatial context method, we should first get and have some deep learning models, because CLAM model is kind of the architecture itself, but we should have something actually more concrete, let's say. So what we need is to have some backbone, a feature extractor, and then the multi-layer perceptron on top of it. We play with different feature extractors, and here we have all of the models that we have trained. And what we can see here is that even though the ranking of the model is different, but actually by the application of statistical tests, we can see that all of the models have similar performance. And this is important because later on we can just compare the results easily. Okay. So we have the models, and now we want to apply the method. To apply the spatial regression models, we should specify what kind of neighborhood size is interesting for us. Please remember that we defined the spatial weight matrix using k nearest neighbors, so we have to know this k. And we applied 4 different variants, ranging from 8, which is the smallest possible context size, to 99, so it's very huge. Please note is that in total then we analyze the context of size actually like 10 over 10 pixels. And the 1 pixel is like more than 200 pixels, over 200 pixels. Okay, but before we apply spatial regression, as I mentioned before, we should know that there is any spatial correlation within the data. So we apply the specific statistical test, which is called Moran's first test. And what we actually have learned is that in almost 100% of cases, we can see that there's a spatial correlation actually. So our first assumption that there is autocorrelation is true, so that we can proceed to the next steps of the algorithm and we can apply spatial regression. Okay, so just to sum up what we do. So we have a fixed test set, and we have 5 trained models. Why 5? Because we use cross-validation during the training time. This is why we have kind of 5 copies of the models. And then we get the feature features for each patch and the corresponding attention scores. And here we have the same color for all features because we have the same backbone always, but we just modify and train actually just the classifier part, so the multi-layer perceptron. And then each of these, let's say, copies are the input to regression models. And we get some performance metrics so that later on we can aggregate them. And we do this kind of procedure for all of the images. Okay, so right now we know how the method works, but why we should care, and why we should actually use it. So this method is useful when we want to test some hypotheses regarding how the neural network works. So the first our question that we posed was whether spatial context is important, so whether this difference in performance metrics will be positive, and also whether there's any difference between these context measures for tumor and for normal data. And here we can see the proportion of the number of cases with tumor and the normal ones having particular spatial context measures. And what we can see is that for the first plot with SCM features, so here we used this W matrix for the features themselves, we can see that, first of all, the range of the values for the context measure metric is the biggest because it's the same x-axis for all of the three plots. And also we can see that the values are positive, so context matters, and it's actually preserved within the neural network. And what also we can see is that indeed there's a difference in values for the tumor data and the normal data. So this is what we have learned, is that indeed the intuition of histopathologists was met, so that tumor, there's kind of context within tumor data. And also what we have learned is that for SCM labels, so when we apply the W matrix for the labels, we can see that the range of values is smaller than in the first case, but at the same time, separability between the values for the tumor and normal data is much bigger. It's like obvious. And lastly, what we have noticed is that the spatial context metrics for residuals is almost always negative. So it seems that the spatial context is not captured within the residuals. So later on, I will only focus on the first two metrics. Yeah, exactly. Okay, so that was the first hypothesis that we wanted to test. And now let's move to the next one. So we wanted to analyze whether the size of the neighborhood, so the K within the K nearest neighbors, is actually somehow related to the values of the spatial context metrics. And what we can see is that if we analyze SCM labels, actually there's a clear decreasing trend, so that the bigger K, the smaller context measure. At the same time, when we analyze SCM features, we can see that depending on the model, it can vary a lot. So it's not that trivial to say, but just to recap, if we want to distinguish between normal and tumor tissue, we should care more about SCM labels. And the conclusion that we got is that, okay, we should apply rather smaller K than the bigger one. And actually it follows the first law of geography, saying that everything is related to everything else, but near things are more related than distant things. So here is something that we could agree on, but we decided that, okay, maybe this is a bit surprising, because we could think of images where this K should be bigger than smaller. And one of these examples is that the tumor is widespread. So we thought, okay, in the previous example, we haven't actually thought about this. And now we decided that we will, let's say, describe each image with tumor by a number, which is a mean Euclidean distance between the patches with tumor. So this gives us information how widespread the tumor is. And we hoped that we'll see that in these cases where the tumor is widespread, then the K should be bigger. And so the spatial context measures should be bigger. And we have the plot for the biggest analyzed K, so equal to 99. And we can see that actually there's no expected relationship, saying that for more widespread tumors, bigger K should be applied. So this is something that we could test that actually is maybe against our first intuition. So far, we use the spatial statistics, let's say, to analyze everything in a global sense. So we expressed whole big image later on as one value. But it doesn't have to be like this. We can also use these methods to analyze the images, still keeping the spatial aspect and having it visual. So we can apply this Moran test that I did at the beginning to test whether we can use spatial regression, also in the local form, where we still have the value for each patch individually. So later on, we can get such plots to analyze whether there are some clusters. And now let me move to conclusions. First of all, what we have learned using this method is that the spatial relationships are kept within the models, and this is especially observed in the case of tumor data. And it aligns with what we have learned from histopathologists. This is something that we aim for, so that the neural networks themselves are kind of similar to experts. And lastly, we have also observed that this context is mostly observed within the local context. This is why this plot that we have seen a couple of slides before had a decreasing trend. And lastly, I would like to point out that the method called Deep Spatial Context is general in a sense that it can be applied to other data sets as well. This is done for the illustration, but it is intriguing fact for the end of the talk is that I don't know if you know, but actually histopathological data in the form of whole slide images is similar to satellite images. Why? Because they're also huge when it comes to resolution. And secondly, they also have sparse labels, so we have like one label per whole big image. This is why this method potentially could be also applied there. So it's like an interesting fact for the end, and this is all. Thank you.